Okay, I'm going to do a screencast here. I'm going to go over the homework from that was due today, Thursday, the 16th. I'm going to go over 4 problems. I did 2 problems I kind of previewed in a screencast that you should have watched before you did the homework. So I'm not going to go back over those, but I will go over 4 other ones that'll help you understand how to do them if you struggled a little bit. The first one is the very first problem in the problem set, and it talks about a jack-in-the-box where the head is compressed down. You know, you got this, I always like to draw a little picture. You got the head is compressed, maybe its relaxed length is up here. I think that's what they refer to it as, yeah, relaxed length. So the spring has been compressed, and the delta X is 8 centimeters. Okay, so the head is released, and they tell you the mass of the head is 50 grams. We got to convert that into kilograms, so that's 0.05 kilograms. They give you the K value of the spring for the jack-in-the-box, 80 newtons per meter. And the question asks, what is the speed of the head? So they want to know how fast is it going when it gets back to its relaxed length. So they're asking basically, as this thing gets to this point right here, you know, this height, what's the velocity at that point? Because that's its relaxed length. So we can do this as an energy problem. So remember, energy, we're looking at 2 different points in time. It's not a movie where we're looking at the whole continuum. It's just 2 snapshots. Initial is here when it's compressed. At this point, all I have is elastic energy, because I'm assuming that this is the point where my gravitational energy, I'm going to set that to 0 at my lowest point. So I have no gravitational energy and it's not moving yet. So the KE is also 0 at this point. Well, now when it gets up to this point up here, at my final point, this is the final position. At this point, it's got some gravitational energy because it's above the original starting point. So I've got some PEG final, and it's obviously moving. They asked the question, how fast is it going? So it's got some KE here as well. So if I just set up my energy equation, that's always the first thing you do with energy, is you set up an equation. So you say PE elastic initial is going to be equal to PE gravitational final plus kinetic final. And now I'm just going to fill in all of the equations for those things. 1/2 kx squared is the elastic energy. mgh is the gravitational energy. 1/2, mv squared is the kinetic energy as it passes through the relaxed position. I know all of these things. I know they gave me the K value. They told me how much it was compressed. I know the mass of the head. I know how high it is. It's 8 centimeters, which is 0.08 meters above where it started. So I have all that information. I have the mass. The only thing I need to solve for is velocity. So I'm going to rearrange this thing to isolate velocity. I subtract mgh from both sides, and then I will divide both sides by 1/2 m. All the 1/2s can't cancel. Sorry about that. All right. So that'll cancel that out. So v squared is going to be equal to 1/2 80 times 0.08 squared, don't forget to square it, times the mass, 0.05 kilograms, times 10 times the height, 0.08, all divided by 1/2 the mass, and then I have to take the square root of all of that. And when you do that, your answer should be 2.14 meters per second if I did my math right. The important part of this problem is setting it up, though, and getting this equation set up based on the situation in the problem. So that's probably the hardest physics thing to do. Everything is math after that. Just setting up the equation and making sure you know at the beginning you have only elastic energy, and at the end you have gravitational and kinetic. That's why I had you do that worksheet yesterday, to kind of get in your mind the way the energy is transferred from one form to another. All right, let's look at the next problem. This is problem 21. I think it's on the second half of the assignment. They give you some information here about a diver stepping off a diving board, drops straight down into the water. So here's a guy on ooh, he's heavy. Sorry about that. He's a big boy. All right, here he is. He lands in the water and he ends up underwater. He's lost some weight by getting in the water somehow. And they tell you he has a mass of 50 kilograms, so he's not that big. And he drops straight down into the water. The water is acting on him with a 1,500 Newton force, and he comes to rest 5 meters below the surface. Okay, this is a problem where all the kinetic energy this guy had at this point right here, all this KE, is turned into nothing. So the velocity here is where he stops. So KE is 0 here. So let's look at a force diagram of the diver while he is in the water. So if I think about the diver while he's in the water, don't forget he's got mg going down, which is 500 newtons. He's got this 1,500 newtons from the water going up. So he has a net force of the 1,500 up, the 500 down. It's 1,000 newtons downwards, okay? So that means that the water's exerting this upward force. Gravity is pulling him down, so it's actually doing positive work on him. So the net amount of work, the W net, which is the important part, is the net force times the 5 meters. Remember that work is F times D times cosine of the angle. And since the net force is upward, it's actually 180 degrees. Because my displacement is downward, my force is upward. So that's 180 degrees between the two. That's cosine of 180 is -1. So the W net is negative 5,000 joules. Okay, so all of this gravitational potential energy the guy had up here is taken down to 0 by this work done by the water. So I don't have to figure out the kinetic energy as he enters the water. I don't have to worry about that. I can just say whatever gravitational energy he had here has gone into, been taken away by the work done by the water. So I can say PEG minus the W equals 0, because I have no energy left at the end. So I have MGH minus that 5,000 joules. So I know that, let's solve for H. So 5,000 divided by mg equals the h. Well, the m and g, h is going to be 10 meters. That's this 10 meters right here, plus the 5 he went into the water. So the total, because they asked about from the distance between the diving board here and where he stopped. So it's not to the surface of the water. So the total is 15 meters. Okay, so that was problem 21. Okay, we're moving on to 22. There's a monkey on a sled here, and he's got an initial speed of 4 meters per second up an incline. I always like to draw a picture of these situations here. So you got the monkey on a sled. Monkey's laying down, I guess. So the monkey's got an initial speed of 4 meters per second. He's going up a 25-degree angle ramp, and he's going to end up somewhere up here. So this is initial is down here. Final is up here. And they give you a mass of the monkey and the sled. And they give you the initial speed 4 meters per second. And I'm going to say he goes a distance d. Okay, and that's what we're trying to figure out. Oh, they also give us mu k is 0.20. So we're trying to solve for the distance that monkey goes. He starts out with kinetic energy. So he has some initial kinetic energy. And at the end, all that kinetic energy is gone. Well, you remember the delta KE is equal to work. So we're going to figure out how much work was done. And the thing that's doing the work is friction. Okay, so you've got your 1/2 mv initial squared minus 0, which is, or 0 minus that, because my final kinetic energy is 0. So my initial kinetic energy has to be equal to the F net times d. And the force acting on this guy is friction opposing us. But it's not just friction, you also have mg, the x component of mg. Remember from our free body diagram or force diagram days, we always have gravity pointed down. We've got components of gravity that act, parallel and perpendicular. Okay, there's our angle 25 degrees. This is mgx, this is mgy. These two are equal to each other. But I also have friction here. Well, since the monkey and the cart are going up the ramp, friction's got to be acting in the opposite direction. Kinetic friction actually acts in the opposite direction. So I've got friction and the x component of gravity that make up the net force for my work. So F net is equal to the kinetic force of friction plus the x component of gravity, which is equal to mu k times normal force. Remember, that's what friction is. That's the friction part. Plus mg, and this is the sine of the angle. Okay? This is the opposite leg of the triangle right here, that mgx. So I have sine in there. And since the normal force is equal to the y component of gravity, that's mg cosine theta, taking you back to your unit 4 days when we were doing Newton's laws. So that's my net force, and that whole thing times d. So I'm going to say 0.2 was mu k, 20 kilograms was m, 10 is g, cosine of 25 degrees plus 20 times 10 times sine of 25 degrees, all times d. Remember, because W net is F times d. So I have d down here at the end. So my 1/2 mv squared has to be equal to all of that. So I have to solve for d. So I'll do that on the next page. Go back and add a page. There we go. Okay, just summarizing what we had on the last page. I've got my kinetic energy initially equal to my net work, which is the change in kinetic energy is equal to the net work. But all I have as far as kinetic energy is initial kinetic energy. So the change and the initial are basically the same thing. So I substituted the numbers in here, 1/2 m times v squared. So my mass was 20 kilograms. My speed was 4, so that's 16 times 20 times 0.5 is 160. The net work was equal to the net force times the displacement. The net force was the friction force, which is this big term right here, plus the x component of gravity, which is this term over here. Friction is mu k times mass, 20 kilograms. Mu k was 0.2 times 10 newtons per kilogram. That's g times cosine of the angle. That's the normal force right there, times mu. Over here we've got the x component of gravity, which is m times g, 20 times 10, times the sine of the angle. That gives us the x component, sine of 25, all times d. Remember, the big mistake students make is they forget to put in or multiply times d for work. So there's 36.25, that's the friction force. 84.5 is the x component of gravity. They're both acting down the ramp. I add them together to get the net force times d. 120.75 times d, and 160 is on the other side. So 1.32 meters is my distance up the ramp the monkey and the cart go. That's a pretty involved problem. I probably wouldn't ask you to do that on a test with friction and gravity going up a ramp, just because that brings back a lot of things that we did in the first semester. But you should remember this stuff, and if I gave you any one part of this, you should be able to do it on a test. All right, last one. On to this one, and this is pretty easy, so this should be quick. The only thing I wanted to point out here as I was going through a couple of the early assignments that were turned in is what this problem is asking for is asking you to figure out, they tell you you've got a 55 kilogram skier at the top of the slope up here, and that's 10 meters above the point B, and it's asking you to set the zero level at 3 different points in A, B, and C. In part A, it says set the zero level for the gravitational potential energy at B, which is our normal place we would put it at the lowest point in the problem, and then find out how much gravitational potential energy is associated with the skier at both points A and B. Well, if B is my zero, then the PEG at B is just 0. And the PEG at A is pretty easy. It's just mg times 10 meters. So it's a positive number. But it's asking to find the difference between the potential energy between these 2 points. So the difference is PEGA minus PEGB. You've got 550 times 10, 5,500 minus 0 is 5,500 joules, positive. We'll repeat it with the zero level at point A. So for part B, this is my zero level. So now PEGA is 0. PEGB is actually negative. It's negative 5,500 joules. And I screwed up. I should have said final minus initial. The difference is always final minus initial. So this is going to be negative 5,500. So it should have been 0 minus 5,500 up there. So PEGB is negative 5,500. Now if we do the same thing in part B, we're going to get the same answer, because PEG minus PEGA is going to give us negative 5,500 minus 0 is still negative 5,500 joules. Okay, between A and B. It's just trying to get you to see that you can have a negative gravitational potential energy if you set your 0 point at the higher level, and then you've got an object that's lower than the 0 point, like in part B. But your difference between those 2 points isn't going to change. The delta PEG is not affected by where you set the 0 point for gravitational potential energy. It's kind of like displacement. If you are going to move in the negative direction 2 meters, then your delta x is negative 2. It doesn't matter where the origin is. Your displacement is still negative 2. Same thing with gravitational potential energy. Okay, hope that helps, guys. Stay home and stay safe.